Hi everyone, I'm Amelia Gregg. I am a Phase 1 NIAC Fellow for 2021 with the idea Ablative arc mining for in-situ resource utilization, or in other words, how to use controlled lightning bolts to mine the moon.
There is a strong desire among humans at the moment to return to the moon, whether it is for scientific curiosity, pushing the boundaries of what we are capable of, or using it as a stepping stone to get to Mars and make humans a two-planet species. There is a need to establish permanent settlements on the moon. At first glance, the moon is a very desolate place that looks like it cannot support active settlements. This leaves us with two options. One, take everything with us, like you would if you were going on a hiking trip in the desert. Or two, find new and creative ways to use whatever is already there. Taking everything with us is not really a feasible option. Earth's gravity is really high, which makes launch costs associated with going to the moon really high as well. This means we have to get creative and use whatever is already there, also known as in-situ resource utilization. Now when we look at the moonscape image like this, we don't just see dirt and rocks. We see places where we may be able to extract water and oxygen, propellants that enable us to refill our spacecraft at our destination, building materials for various structures and habitats, and even metals and silicon for making semiconductor electronics like solar cells on the moon. All we need to do is extract the raw elements from the lunar regolith, or the lunar soil. Lunar regolith is comprised of many elements, including oxygen, silicon, aluminum, calcium, magnesium, titanium, and many, many more. It has also been confirmed that there is water ice frozen into the lunar regolith in certain places on the surface. These are mostly confined to regions that receive little to no sunlight, leading to the water deposits being located in clusters in permanently shadowed regions in craters around the south and north lunar poles. Water is the main focus for early mining missions to the moon, as it can be used as water, refined into pure oxygen, or separated into oxygen and hydrogen to use as propellants for spacecraft. As the highest concentration of water deposits occur around the lunar South Pole region, that is the focus for early mining missions. There are many challenges associated with mining the moon. Not only is it a long way away with expensive and volume-limited Earth launches, but the permanently shadowed regions where the water is are really cold and really dark. The lack of sunlight especially means that direct solar power cannot be relied upon. There is also negligible atmosphere on the moon, and gravity is significantly lower than on Earth. Fluids such as gases and vapors will not behave the same way as they do on Earth. There is no option for high flow rate or pressure-driven flows, and this results in large losses through natural diffusion processes. Also, the lunar dust is very fine and electrostatic. It sticks to absolutely everything and makes moving parts a really big risk of clogging. The ablative arc mining approach offers a potential solution compatible with all of the challenges associated with lunar mining. The process begins with an electric arc being excited across the surface of the lunar regolith. The electrons in the arc will ablate off all different kinds of materials from the surface of the regolith, and they will come off in charged form, which means the ablated material can be handled using electric and magnetic fields. As an added benefit, the arc is solid state and requires no moving parts to extract these materials from the lunar regolith. Being charged, the ablated material can then be directed towards a collection unit using electric fields. This minimizes natural diffusion losses in the low-pressure ambient environment, and it has no reliance on gravity-related forces such as convection. Once inside the collection unit, the ablated material is focused into a collimated ion beam using ion optics. Ion optics are a series of charged apertures that control and focus charged ions in the same way that light optics control and focus photons of light. The result is a beam of ions all moving in the same direction and with equal velocity. Moving equal velocity is important for the next step, which is to pass the ablated material through a constant magnetic field. When charged particles traveling at uniform velocity enter a magnetic field, their paths will bend, with the radius of curvature proportional only to their mass. This allows us to sort the ablated material by mass. The various ablated elements can then be collected into dedicated collection reservoirs placed into the path of the particles. As each collection reservoir only collects one kind of element, it can be designed specifically to maximize collection rates. For example, water can be collected in a cold trap where it is returned to ice form. Carbon dioxide or other gaseous materials can be collected in reservoirs containing zeolite that readily traps gases at low temperatures. And metals or other solid materials can be sputtered onto the surface of a collection plate for later removal. All of these components are sufficiently low volume and low mass to be contained on a single mobile surface crawler. This compact system can then extract, sort, and capture multiple elements simultaneously, and being mobile, can mine over large areas. To deploy the system on the Moon, the crawler is placed in one of the South Pole craters containing water. 12 arcing electrodes are placed around the ring on the front. The ring is placed on the ground so the electrodes make contact with the surface, and the arcing begins. Successive arcs ablate away a circular region under the ring. Ablated material is drawn into the crawler through a hole on the front, ready for collection and sorting. Once the regolith under the ring has been ablated to a depth that the arcs no longer reach the surface, the crawler raises the ring, moves to a new location, and begins arcing again. Once the collection reservoirs are full, or the crawler needs to recharge its power, it moves to a crater floor processing interchange. The full containers are taken by conveyor or other similar technology to a processing plant on the top of the crater. Empty containers are sent down to the crawler so that it can resume mining operations. Based on what we currently know, a small-scale demonstration system with a 10-centimeter arc fired at 1 Hz can ablate up to 131 kilograms of material per year for a continuous power input of 75 watts. Scaling this to collect 10 metric tons of material per year, as would be needed by early lunar settlements, would require a total area of 76 meters squared to be mined per year. This scaling can be achieved by both increasing the radius of the arc and using more than one vehicle to mine multiple areas in parallel. For example, a larger crawler with a 50-centimeter arc fired at 1 Hz can collect over 23 times more material than the small system, and 4 of these crawlers operating in parallel would be able to meet the 10 metric ton requirement.
One of the biggest unknowns is how lunar regolith behaves under the influence of an electric arc. To test that in this phase 1 effort, we are taking lunar regolith simulant, placing it inside a thermal vacuum chamber that can produce low pressures and temperatures similar to that found on the surface of the Moon. We place 2 electrodes into our regolith, pass a high voltage between them to incite the arc across the surface. We are now capable of producing controlled, repeated arcs across the surface of lunar regolith simulant, and are working on the next phase of the experiment, which is to measure the amount and type of material that is being ablated off under the influence of the electric arc. Once we have this information, we can use it to update our collection rate and power requirement estimates for an ablative arc mining system deployed on the Moon. And that will allow us to make a better comparison between how our system will operate and other proposed lunar mining techniques, such as thermal mining. Although there is still a lot to investigate, an ablative arc mining system can simultaneously extract and capture and store multiple lunar regolith materials in a single system. It requires no moving parts except for a 1-axis robotic arm to raise and lower the electrode ring and a standard rover drivetrain for mobility. The use of electromagnetic fields to control the extracted materials maximizes collection rates in the challenging lunar environment. If you would like more information about this system or to stay up to date with our progress, please follow the EMU Aerospace social media or periodically check out our website. You are also welcome to reach out to me personally through email, social media, or LinkedIn at any time.